Myself Deepak Maurya, and today I am going to teach you about the compression test. Today I am just going to teach you about the theory. In the next video I will show you the experiments. So there are two types of machines. One is the screw driven, another is the hydraulic actuated. In the screw driven, this column is having the lead screw inside it, which is having the threads, and this crosshead is moved up or down with the help of this screw. In this machine, this lower platen is fixed. This lower platen is fixed and the upper one is moving. This is the load cell. These are the grips for the compression test. This is actually a linear Solson machine, and this is the hydraulic actuated which is now acquired by the Instron. Is generally the hydraulic actuated. In this also either the top crosshead will move or lower will move. Okay, so one will be fixed. So in this case I am saying the upper one is fixed and lower one is moving downward. Okay, and this is actuated by the hydraulics. So there are two types of machine. One is a screw, another one is a hydraulic. We are going to see what are the input and output we are getting from the machines. So in the terms of input, if you will say, we have seen that we are providing the displacement in the terms of screw driven or the hydraulic actuated. So due to this displacement, the load cell give us the force. So from the machine we are getting the force and displacement. So we will get the force 1 Newton, 2 Newton, 3 Newton and so on, and for each force we will get the deflection. So these are the two data we will get from the machine, and we can plot it in the force versus displacement graph. Force, it may have the unit Newton or any kilogram force, displacement in mm. So this is the displacement. So we can get some curve here. Okay, either linear or it may be any other shape, just I'm doing arbitrary. So from the machine we got the two data, the force and displacement. But we are not interested in force and displacement. Why? Because this graph depends on the size of specimen. If we have took the larger size specimen, the required force will be higher. Okay, so we need the another term which can independent of the size of the specimen. So what we are going to use, we are going to use the term stress. Stress is equals to force by cross-sectional area versus strain. Strain is equals to del by displacement by of original length. What is this? Actually this is the specimen, and you have loaded with this face parallel, that is a cross section. This is the cross sectional area we are going to take. This is the width B and this is the width W. This is the height or thickness. So the cross sectional area is B cross W and this is equals to del y of t according to this specimen. So by this we are getting the terms stress and strain, which is independent of the size of the specimen, and we can draw the curve easily. But again here there is a one problem. Is this deflection del? Is it the correct what we got from the machine? Is the deflection what we are writing here, is it correct? No, it is not correct. We need to modify it. How we are going to modify it? I have asked you whether this del is correct or not. So this is not correct. So why it is not correct? We have to first answer. Actually, when the specimen is loaded between the grips, this grip is connected to the crosshead with the help of some pin. If this pin is having some gap, so for example 0.1 mm, that will be count in the displacement. If it is the screw driven machine and the screw and the crosshead is having a play of 0.001 mm, that will also count in the displacement. If it's a hydraulic actuated, if there is a play due to that hydraulic actuators, so that will be count into the displacement of the specimen. So how to avoid that one? To avoid that one, we are going to use the compliance correction. What we are doing in the compliance correction? Actually, if you have seen in the tensile test, we are using the extensometer, which is giving the displacement in the predefined region, or we are using the DIC in the compression as well as in the tensile test. So we can use this types of one equipment also, but extensometer are generally for the tensile test. For some cases it is for the compression, but the best one is that to find the compliance correction, to do the compliance correction. How we are going to do the compliance correction? We can we can load this flat grips or any other grips of the machine without any specimen, just like these are the two grips which are uh, touching each other, and we are going to load it in compression. When we are going to load it in the compression, so and when we are going to load it, be careful, its cross head displacement should be lower. Cross head displacement you can provide 0.01 mm per minute, and when we are going to load the platen without any specimen, we will get the load deflection curve. We will get the load deflection curve. And this is very important to understand. This force is the force of the machine, deflection of the machine, and from here we will get a curve, and this curve is linear. The reason is that when we are going to press these grips are designed so that it should not yield for that specified load. So from this force versus displacement graph of when we are loading the platen without any specimen, we will get the stiffness from this graph. K. K is equals to force pi of del, or when we are doing without any specimen between, that is the force of the machine and deflection of the machine. And we can say the compliance of the machine. The compliance of the machine can be find out by 1 by of Km, that is del m by of Fm, that we will get from the curve, from the data of the force versus displacement of the machine without putting any specimen between the grips. From here we got the compliance. Okay. Now when we have this compliance, now we can go and do the test with the specimen. Here you can see we have keep the specimen in between the platen, and we are going to press it with the force F. From here we will get the force, total force versus total displacement. So actually this displacement having the extra, this displacement is equals to displacement of the specimen plus displacement of the machine. So for the specimen, displacement of the specimen is from the total we have to subtract the displacement of the machine. So how we are going to do this part? So we know the displacement of the specimen is equals to total displacement what we got directly from here when we have done the test of the specimen, when we have done the test with the specimen in the grips, minus the compliance of the machine into the force, total force at which this displacement is there, because from here we know we will get some curve. Okay, whatever the curve, I am not interested in that one. So I have got some displacement delta t at a particular force. Okay, so the displacement of the specimen is equals to this delta of total minus compliance of the machine into the force at that displacement. Similarly, at each point, actually we are getting the displacement for each force. So we can directly put it in this Excel sheet and we will get the displacement of the specimen, and from here we can draw the force versus corrected displacement, and from here, from this curve, whether this is the linear or any other curve, from there we can find the modulus of elasticity through this, model of elasticity we will get force by area, and that is del corrected by of thickness. Okay. For the stress is actually independent. Stress, if you find out the yield stress, ultimate stress, this stress is actually independent of the compliance, does not have any effect. If you want to find the yield stress or ultimate stress, so you can find the maximum, for the case of ultimate stress, you can go and find the maximum force and divide it by the cross-sectional area of the specimen. But if you want to find the modulus, then you require the corrected displacement divided by of original thickness. Okay, friend. So friend, I am just going to revise what we have done till now. So first we have to find out the compliance of the machine. How we are finding the compliance of the machine? We are doing the test on in the machine, compression test without any specimen, and we are getting the curve of force versus displacement, and from this curve we are getting the stiffness of the machine is 1 by of compliance of the machine, that is the Fm by del m. If we know the compliance of the machine, now we can go and do the test on the machine with the specimen. Now we have keep the specimen between the plane and we are doing the test. From here we will get the total force Ft and delta T. Okay, but we know that this is not correct, and so how we are going to find out the corrected displacement or the displacement of the specimen, that is by the what we got it, the total displacement minus compliance of the machine, but we have got it from here, into the force at the position of the displacement. From here we will get the corrected displacement of the specimen. Okay, and when we'll get this one, we can go and draw the stress versus strain curve. Okay, this strain is based on the corrected displacement, and from here we can find out the modulus. Modulus is equals to force by area divided by del corrected by thickness. Okay, so we have learned till now here. But during all of these things, we have seen the rate of the crosshead displacement, the size of the specimen. So how we are deciding all of these things? Actually, that is we are deciding with the American Society for Testing and Material. That is the ASTM. It is the international standard organization that develops these standards, and it is the world's largest international standards developing organization. In India, we are using the Bureau of Indian Standards. Okay. So we have seen that we are doing the compression test. In the compression test, there are so many ASTMs. So which ASTM we have to follow? The ASTM depends on the sample type, generally the material, and the sample type. Which type of samples we are going to use? For example, the cellular plastics. These are the polypropylene, polyethylene. Okay, this kind of samples. Okay, for this we can use the ASTM D1621, that is standard test method for compressive properties of rigid cellular plastics. Okay, but here I have written the wood. The wood is having a different ASTM standard that you can just search on the Google. You will get the ASTM for the wood. For a rigid cellular plastic, the size of the specimen should not, the cross-sectional area should not be less than 25.8 centimeters square, and should not be more than of 232 centimeters square. The height of that specimen is this one, that is 25.4 mm, and maximum height should be less than or equals to the diameter of the specimen. Okay, how they are deciding these conditions? Actually, they are deciding these conditions to avoid the buckling of the specimen. When we are loading the specimen, if this specimen get failed in the buckling, then the results are wrong. Then we have given the wrong data to the company or the machine, to anyone. Okay, so we have to be aware. So actually ASTM reads all these things, where the stress concentration will be more, up to which reason. So they are changing the shape, size, and they are giving us a certain size of specimen. Okay, for this ASTM, they are saying that we have to use the 2.5 mm per minute of cross-head displacement. Similarly, we have the different types of AST. For example, the rigid plastics. In this rigid plastic, we have the acrylic, we have the composites material, Okay, we can use ASTM D695 for the standard test method of compressive properties of rigid plastic. They have again given a specimen size 12.7 by 12.7 into 25.4 mm. For prism, if we have the shape is cylindrical, then 12.7 mm in diameter and 25.4 mm in height for the cylinders. Okay, and they are saying the slenderness ratio should be 11 to 60 is to 1. Okay, how they all are deciding these things? Slenderness ratio, I told you, to avoid the buckling, they are deciding all of these things. Cross-head displacement is 1.3 mm per minute. Okay, sometimes in some cases this is in the terms of this test should be finished in the 5 minute or less than 6 minutes, something like that condition. Something I have told, in composites are generally the thinner. Okay, in that case, how what we can do? In that case, the size of the specimen this ASTM has mentioned, and they have also mentioned the fixture. That fixture I will show you while doing the experiment. Okay, if we have the sandwich core type of sample, or the any natural fiber cellular sandwich core just like the aluminum honeycomb. Okay, I have already shown you the natural clean cellular core in the above graph. Okay, here you can see this is a natural sandwich core, in which these are the core of the plants, which is filled with the polyurethane, and we are doing the compression test on it. Okay, so this type of test material is there. Then the size should not the shape should be square or circular. Cross section not exceeding, its cross section area must not be more than of 10,000 millimeters square. Okay, cross head movement, they are saying the test should be finished in 3 to 6 minutes, or they have suggested 0.5 mm per minute of cross-head displacement. When they are saying 3 to 6 minutes, then how we will come to know at what cross-head displacement with this time will be occur? So for that we are doing the one rough test, and by doing that rough test, if if I have chosen the x mm per minute, I have done one rough test and I found the ultimate failure is occurring in the 8 minute. So I know my this condition has failed, so I have to, for this giving the 8, so we have to increase it. I have to x plus something. Okay, so that it should fail the material within the 3 to 6 minutes. Okay, that is a different type of ASTM standard. How many number of samples we have to do the testing? We have to do the minimum 5 number of specimen according to ASTM, and sometimes if we have a crisis of the number of samples, in that case we will see the stress strain curve, and we will see the repeatability. if we have done the three tests and they are the repeatable, okay, if they are the repeatable, then we can say that we have done the three tests and three out of three, all of them are having the repeatability, then it can be accepted. Okay, so that is the one thing. Okay, why to use the grease or lubricant on the plate? Actually, this question I want to answer in that while doing the experiment, but I'm answering it here. Okay, for the when we have the platent here and it is the specimen between them, when we have applied the force, actually there is a friction between the specimen and the platen, and due to that it will bulge outward due to this friction at the top. Due to this friction it will the friction between the platen and the specimen will not allow it to move outward, so there will be a restriction and in between it is moving out. So the bulge is there instead of it is the like proper expansion in both directions, there is a bulge out. To avoid that situation we have to put the grease on the top and bottom or any other lubricant which should not affect the material specimen. Okay, in this part of the video I am going to tell you how to process the data. Okay, we have got the force versus displacement graph, and from there we have plot the force by area, that is the stress versus the strain curve. Strain is equals to corrected displacement by time. So first type of curve can be the curve. First type of curve can be like this. Okay, so from here we have seen that this is the reason. This is the toe reason. There are so many reasons for this toe reason. If we have any material and we are going to compress it, for example, it is a honeycomb structure or the cellular plastic, so there will be the some space between the molecules or that particular prop for that particular material. So when we are applying the force, the space between them are going to fill by the movement of this, and they are going to fill this space. So the two reason is generally goes and fill that space. So we are generally avoid this. How we are going to avoid this? We are just extending this linear region up to the strain. Okay, we are just extending and we are considering this as the starting position of the strain. So what we can do? We can shift the graph actually. We can uh, we can go and subtract this much of strain from the corrected strain. Okay, so from here now we can go and find out the models. Okay, so when we are calculating this modulus, we have avoid this the first linear smaller region, and in which cases we can avoid actually whenever this stress value, okay, at this stress sigma dash, whenever this sigma dash is less than of the sigma maximum, we can avoid this portion by drawing by extending this linear region up to the zero stress. Okay, and for finding the yield stress. Yield stress is the stress up after the linear region where the material has starts to yield. Okay, in many cases the people take it at differently. So generally we are in the for example for these cases it is the ultimate strength because the yield and it is going to be failed somewhere here, then it is yield and ultimate stress is the same, that is the maximum force by area. Okay, and we can find out the E, that is stress by characteristic. Okay, but in some cases the curve is maximum cases actually. The stress strain curve is like this. Okay, so here the three regions are there. First one is the linear region. Second one is the plateau region. Third one is the densification region. What is generally occurring in these three regions? If you will see, in this region, the material is up to here it is elastic, linearly elastic, means if you will unload it, it will be follow the same path. After that, yielding has a start for the same stress, it is expanding, it is it is compressing, and when it is completely get for that stress, when there is after sometimes it has get all the spaces between the specimen get filled out, then what happened, then it is get rigid actually, all the space get filled out. Or then if you will still apply the load due to the densification of this material, okay, the platen getting start to take that load, and that's comes in the densification actually. The material also start to densify. It is already during this part when they are compressed. For the same stress, there is a strain. What is this strain? This is actually going and the material is compressing and the space between them can completely get filled up. It is making the material rigid. So this is a after as soon get densified, this will be going to be the stresses is going to be start very increase very large. Okay, because in these cases the platent is also going to take the load. Okay, so thank you, these types of material are there. And actually the last thing is this one key, or in these types of the yield and other types of stresses, we are actually specified in the terms of at what percentage of strain we are going to take. For example, up to the stress for the 10 percentage of strain, or 2 percentage of strain, or just up to the linear region. Okay, so like that we are mentioning the stresses in these cases. Okay, thank you students. I think you have enjoyed the video. In the next video we are going to learn the experiments